Hi, we're Senior Design Group 18, the Motorcycle Heads Up Group, and this is our final presentation.
A motorcycle helmet will receive data, speed and RPMs, wirelessly and display the information on the visor to create a heads-up display. The purpose of this project will be to reduce the amount of time spent looking at the gauges on the vehicle. At high speeds, looking at the gauges for even less than a second will mean the rider has traveled many miles blindly. Unlike cars and trucks, motorcycles do not have onboard diagnostic cables, or OBDs. Only the newer motorcycle models will have this new technology. Now, the project will require our sensors to measure the speed and RPM, since we're unable to get that data from the bike itself. And since we have speed and revolutions per minute, we're able to calculate the gear the motorcycle is currently in. Now, the motorcycle helmet will utilize transparent displays so as to not block the vision of the rider. We've considered using OLEDs, which are organic light-emitting diodes. However, most of these are commercially unavailable. EL ink was another design choice we thought about. However, there are very few resources regarding the usage as a display. Therefore, we went with a custom surface mount LED display mounted on a transparent dielectric.
Okay, the first block we're going to be talking about in our overview is the on-bike enclosure. For on-bike enclosure, we just bought a project enclosure from Radio Shack. The only changes we made to it was we drilled a hole on this side for its power switch so we could turn the power supply off. And then on the back, we also have some holes for our wires to exit for the sensors on the bike. What's inside this is the power supply for the on-bike circuitry, microcontroller, transceiver, and then also all the circuitry involved for the sensors. That's Hall effect sensors, tachometer, and light sensors. Next, I'll talk about the power supply, which I said before is in here. The power supply basically is just a 3.3 volt linear regulator. The only external components are a cap on the input and output. And then also that linear regulator is then powered by 3 AA batteries, which are inside here as well. The next block we'll talk about is the Hall effect sensors block, which actually includes the Hall effect sensors that we use for speed, as well as the tachometer circuitry. So for the tachometer circuitry, our sensor is actually just a wire that we wrap around the spark plug wire. That then sends a noisy signal that is then filtered by this external pack that we bought and then sent to the micro, and it's sending basically a 3.3 volt square wave. Then we use that to determine RPMs. Then for the Hall effect sensors, we mount this Hall effect sensor near the back wheel, and on the back wheel we have 4 magnets of alternating polarities. So it'll see a north pole and it'll jump up to outputting at 3.3 volts. And then it sees the south pole, it goes back down to 0 volts. So it's effectively a digital magnetic switch, and we use that to generate a 3.3 volt square wave, which we use to calculate the speed of the bike.
Also in the motorcycle subsystem are the light sensors. So they show when the blinker, the right and left blinker are on, as well as the brake. These are powered by a power supply on the motorcycle side, and those outputs are then taken to the microcontrollers, and they're sent to the helmet's display.
Both microcontrollers and transceivers are powered through their respective regulators. Now, the motorcycle side is going to take in data from the motorcycle, as in the light sensors, the Hall effect sensors, and it's also going to take in the data from the external tachometer we had to hack into. Now, it's going to send that data through to the helmet subsystem, and that helmet subsystem is going to control the display using its display logic code.
The microcontroller is powered by a 3.3 volt linear regulator power supply, which is powered by batteries on one end and then outputs a 3.3 voltage or 3 volt signal to both the microcontroller and the display. The display has 2 parts: the display logic, which is made out of simple BJTs, has switches, and a microplexer, a multiplexer, and those signals are sent from the microcontroller and controlled there. And then those go to the specific characters, which are made out of our surface mount LED custom display. And all of that is wrapped into a nice enclosure here. As you can see, it's a box we got from DigiKey with a switch for power on and off and a hole for the transceiver's antenna. And this is attached to the helmet through a camera support system. This is a camera support system for the stealth camera, widely used in motorcycles. And that keeps it nice and secure and easy to do. And so that's our block diagram.
So a lot of people kept asking us, why did we use Zigbee as our communication protocol? Bluetooth was another design choice we were considering. It is more than fast enough, but people that we know who have used it in the past have had difficulty with it. We're only transmitting data every 1/10 of a second, so Zigbee is more than enough for us.
So for our light sensors, we had a photocell here and a resistor in parallel, and those two we had in series with another resistor. What this did was allow us to take our voltage output across the parallel and resistor and make sure that our voltage was always between 0 or half VDD and it was not dependent on the photocell itself. And this made sure that our voltage range for our output was lower than the ADC maximum, making sure we don't damage our microcontroller.
So a unique design choice we were considering for the display was using EL ink, but that didn't really pan out. So we decided to switch to surface mount LEDs. Now, each segment for each character is made up of 3 0603 packages. Now those are really small, so we had to individually solder them underneath a microscope, and then individually place them onto Scotch tape. That's it. The way to connect them was using uninsulated wire to give the smallest diameter.
This worked great for our prototype, but we in the future like to put the display on an actual PCB using transparent materials such as this. For our tests and our demonstration, because our system is used for a motorcycle, we can't do it in lab. So we're going to cut to some videos that we've taken in the field with the motorcycle.
So we have Curtis right there, and we have our motorcycle subsystem right behind him. Here's our speedometer of the car, and we're going to be following him, and here's our speedometer of the system. Okay, going 35, 34. Okay, now he is really right next to us, and we're going to be trying to keep his speed. 33, 33, 35, let's see, there's 34, 34, 34. So yeah, it's matching up. Okay, we're going to be speeding that. How much road do we get? I don't know. Okay, so he's right there. We're going to be matching our speeds now. 45, 44, 45, 43, 44. Okay, we're really close. Okay. There's a 59, 56 there. 58, 58,
Okay,
60s.
it's 35, so we're going to slow down.
Okay.
That's our speed. That concludes our speed test video. Now we'll go on to our tachometer video.
Alright, so that's around idle, and we're about 800, 900, and we found out the scale is around, let's see, 150% of our value. Okay, let's start revving.
Okay, so I can switch hands. Okay, so the rev.
Okay, up slightly. One more time. Okay. This next test shows our turn signal indicators and brake signal indicator.
So we have our sensors right now on the right and signal brake and the brake. And then we're going to move up here to the front where we have the helmet, and you'll see when we pull this brake lever that the light will turn on. So you can see it there. It's really small, hard to see, but it's in the center. So that's the first one. Turns off. 2, 3, 4, 5. Now we have the signal, the right signal over here, so we're going to turn it on, and we'll see. You have to move your hand to the right a little bit so we can see it. Here, 1, 2, 3, 4, 5.
As far as tips for next year's senior design students, I'd say make sure when you're picking your groups that you guys all have a variety of interests, because like every project's gonna have power in it. Like every project's gonna have to have a power supply. So make sure you don't have 3 group members that hate designing power supplies and stuff like that. Another thing I'd say is make sure whenever you can, try to keep your design simple so that it's easy to test, and that you want to try to keep it as low cost as you can, because depending on your project, $300 might be pretty tight, and you don't always have time or money to change your design and buy something new and then have parts that you don't even end up using that you spent money on.